Welcome. I'm Bill Milroy, Chairman and CTO at ThinKom Solutions in Hawthorne, California. In this workshop presentation, we'll discuss some of the current and trending considerations when designing and deploying modern SATCOM phased array antennas and terminals. So let's get started. We'll begin by discussing satellite constellations in general, touching on both GSO and NGSO types, along with their key characteristics and their distinctions. We'll briefly discuss operating frequencies and then dive into a brief discussion of phased arrays, their various types and their attributes. We'll cover key antenna terminal figures of merit, including gain, G on T, EIRP, scan range, and bandwidth, along with key component and RFIC characteristics, such as noise figure, front-end RF losses, and power outage efficiency. Another important topic, particularly as more and more satellites are deployed, are the design and operational concerns with respect to interference and interoperability, particularly with increasing densities of satellites and increasing sharing of limited frequency resources between the various satellite constellations and even the competing terrestrial users. We'll then move on to discuss key SATCOM terminal markets and platforms, from space to air to land, and even on and under the sea. Finally, we'll summarize how various phased array characteristics map to the corresponding requirements and what these mean in terms of current and evolving demands on LNA, HPA, and RFIC components. You'll likely recognize most, if not all, of the names on this chart, including well-known established GSO, that's geosynchronous orbit companies, as well as new players, particularly amongst the NGSO, that's non-geosynchronous orbit companies. In terms of the latter, some of these companies no doubt will successfully overcome all of the various technical and business challenges in coming months and years, but likely some will not. At this point, it's difficult to pick the winners and the losers and to accurately predict what this chart might look like 2 or 3 years from now. You'll notice that many of the GSO players have NGSO plays or partners, or at least license applications. And perhaps less clear, many of the NGSO players have GSO collaborations as well. What's clear then is that modern SATCOM terminals will need to agnostically address both GSO and NGSO constellations and ideally provide flexible agnostic support across the various players and the companies in each. This is going to be a big challenge. Okay, here's an example of a representative NGSO system. In this case, this is Telesat's Lightspeed constellation. The LEO, or Low Earth Orbit System, which will be initially launched in 2022 and will employ both polar and inclined orbit satellites to make up the constellation. Other examples, of course, include SES's O3b and mPOWER, which is a MEO, medium Earth orbit system, as well as several other deploying or planned to be deployed LEO constellations from other companies I'm sure you've heard of, like SpaceX, Starlink, OneWeb, or even Amazon's Kuiper, and there are others too. Unlike more traditional GSO satellites, which by design service specific geographic and or maritime areas via wide area or spot beams, LEO and MEO constellations generally cover much, if not all, of the Earth's surface. This is indeed an advantage in terms of global coverage and lower latency, but at the disadvantage in terms of number of required gateways and teleports, which must be similarly deployed globally as well. There's also the associated higher net satellite and launch costs with so many extra satellites as compared to GSO, as well as some of the unique satellite management challenges in terms of power and thermal management. As you recognize, the satellites transition between sunlight and darkness every 90 minutes. Okay, and here's an example of a hybrid, a mixture of GSO and NGSO satellites constellations, which can work together collaboratively in order to realize the specific density benefits of GSO systems, along with the lower latency and the true global coverage advantages of NGSO. The ideal SATCOM terminal then is one that can efficiently tap and utilize all of these various satellite resources. Aeronautical in-flight connectivity is an excellent example where aircraft routinely require seamless internet connectivity, both regional as well as intercontinental, i.e. over the water and over the pole routes. Hughes has an extensive GSO North America constellation and South America coverage as well, and this will soon be augmented with SES's GSO SES-17 satellite. When combined, in this particular example, with SES's O3b and mPOWER MEO satellites, along with Telesat's LEO constellation, the result is an extremely versatile and robust, truly global capability. This is, of course, only one of the many hybrid networks in the works. There are, of course, others. So as compared to GSO systems, which by definition have one specific inclination angle, i.e. 0 degrees, they're equatorial, and have one specific orbital altitude, i.e. the geosynchronous altitude, namely about 36,000 kilometers, NGSO satellites have additional design degrees of freedom in terms of orbital altitude, could be anywhere between 400 kilometers and 8,000 kilometers, and inclination angles, namely they could be equatorial, they could be polar, and oftentimes there's something in between, meaning an inclined orbit. Additional NGSO design drivers include the gateway and teleport support. Lower altitude satellites generally require more teleports, of course, and constellation sizes, which can vary from a few hundred to even tens of thousands. So prudent selection of these degrees of freedom then dictates and leads us to operational characteristics, such as minimum elevation angle. That's for a given Earth terminal, it's important that we don't have to go to too low an elevation angle. The visibility period, which that could be anywhere between 3 and 40 minutes, depending on the altitude. The beam coverage footprint, which are very specific to the different constellations. The slant range versus the terminal size. So typically the terminal is going to need to be sized for the longest slant range, which is the most difficult link budget to close. And of course, depending on how low we go in elevation angle, generally those would correspond to larger slant ranges. Latency is a key characteristic, key advantage of NGSO satellites. I'll talk about that a little bit in an upcoming slide. I already mentioned gateway support and density. If you have if your satellites are going and providing global coverage, the bad news is that means you need gateway support that's also global, which could mean hundreds and hundreds of individual gateway systems to backhaul information from the satellites. And then making the news, there's lots of concerns about collision, as in collision between satellites or collision between satellites and orbital debris. And that's, of course, going to become an increasing concern as we move forward. There's not much the terminal can do about that, but it is a consideration in terms of the health of the whole ecosystem. And then RF interference considerations. This isn't really collisions in terms of physical collisions, but collisions in the sense of one satellite's beam hitting another satellite beam, two satellites using the same frequency band interfering with each other, satellites interfering with terrestrial users using the same frequency bands. We'll go into this in a little more detail, but it's pretty crowded out there. Okay, on the topic of latency, this is a really important distinction between GSO and NGSO satellites. Everything else being the same, low latency is better than higher latency, though most all of today's SATCOM applications, including voice, internet, streaming, etc., have obviously found a way to manage the 700 to 1200 millisecond latency or delay or ping time associated with established GSO systems. That being said, NGSO systems, owing to their considerably lower orbital altitude, can push latencies down to the 30 to 150 millisecond range, depending on their altitude. And that can improve the quality of service of many of these same applications and dramatically improve user experience in certain latency sensitive applications like gaming, electronic trading, etc. However, ultra latency sensitive applications, those requiring under 30 millisecond latency, such as machine to machine, MTM, virtual reality, self-driving cars, so on and so forth, or even elite gaming and even elite electronic trading are necessarily going to remain outside of the reach of satellite-based systems just based on physics. So instead, those are going to rely on the terrestrial-based transport layers, including fiber, point-to-point, microwave, and MIMO systems. Okay, another important design consideration and trend is selection of the frequency band of operation. C, X, and KU bands have been the traditional bands of choice over the past decades, and they certainly are not going away, though a portion of C-band was recently repurposed for terrestrial 5G use. However, over the past decade or so, Ka band has enjoyed increased adoption based on its shorter wavelengths, which in principle allows for smaller sized antennas on both the user and satellite ends, but at the expense of increased sensitivity and potential outages in heavy weather and rain. You'll notice that Ka band also enjoys somewhat larger bandwidth allocations, particularly in the transmit uplink direction. However, there may well be a new revolution coming as available Q and V bands are beginning to be adopted for SATCOM uses. This has already begun in military user terminals as well as gateway teleports that backhaul commercial satellites. You can see that the available bandwidths in Q and V bands, 24 gigahertz in total, represents a huge opportunity to dramatically increase frequency bandwidth. And of course, then that increases attainable data rates and throughputs for SATCOM systems and the terminals themselves. We see this as a really important trend moving forward. In terms of phased array technologies, the playing field includes a broad range of architectures, componentry, and techniques. Referenced here is an excellent recent 2020 overview of a subset of these technologies by the European Space Agency, in this case covering technologies specifically from the EU. Architectures include passive phased arrays with centralized LNAs and HPAs, and active ESAs or AESAs with distributed LNAs and HPAs dedicated to individual radiant elements or small groups of elements. Some phased arrays even downconvert directly at each element, while others employ digital beamforming techniques. Requisite phase shifter or beam steering functions can be pseudomechanical, metamaterial-based, or MMIC-based. Thinning is also sometimes employed in order to reduce the number of radiating elements as a trade between lower cost and higher side load levels. Phased arrays are also termed as half duplex or full duplex, depending on whether or not they use a separate or common apertures for transmit and receive functions. Full duplex allows for simultaneous transmit and receive data streams, whereas half duplex systems have a common aperture, receiving 60% of the time and transmitting 30% of the time, typically, and using about 10% of the time to switch between the two functions. In terms of specific companies and technologies, and this isn't an all-encompassing list, here's a partial list of phased array suppliers, along with their respective technology bases and product status. Also shown is the specific market or markets addressed by their products. We'll talk about more about the markets a bit later, but you can see that in some markets, there's definitely segmentation between military and commercial users and between various platforms. This is certainly not a comprehensive representation of all the various phased array products, but here are a few specific examples from ThinKom, Boeing, Isotropic, Satisfied, NextCom, SpaceX, Starlink, Hanwha, Phasor, Ball Aerospace, Kymeta, Galat, and Alcan, and that's just a subset of all the ones that are out there. Please don't be angry if I left someone out. So in the upper left is a ThinKom VIX phased array, and you can see there's Boeing arrays. The isotropic array is shown on the right, which is a lens-based system. You can see in the very middle there, the Starlink terminal, which actually is mechanically skewed in the direction where the satellites are and then electronically scanned. That's a new antenna on the market. Lower left is the Ball Aerospace antenna. Kymeta has enjoyed some market adoptions as of late. And I've shown Alcan in the lower right, Galat, but this is not intended to cover everyone, but just give you an idea of the diversity in the phased array ecosystem. Okay, so generically speaking, and by that I mean regardless of the phased array type, front-end ohmic loss, LNA noise figure, and scan efficiency, phased array gain, loss versus scan angle, are the key drivers to overall G-on-T performance of any SATCOM phased array. Now, the G-on-T metric is dependent not only on lost gain via RF losses, which diminishes the gain term in the numerator, but also on elevated noise via the impact of ohmic losses and LNA noise figures, which appears in the denominator. Hence, the quotient G-on-T is dependent on both. This chart quantifies a range of values across the different antenna types, including both parabolic dish antennas, AESAs, passive ESAs, along with ThinKom's VIX array. So let me just talk about the metrics here just for a second. You'll notice area taper loss, that's how efficiently the active area is used. I mentioned thinning as an option that's employed in some but not all systems. Spillover, which applies only to dishes. Blockage, which generally applies only to parabolic dishes. Ohmic loss, which would be the diplexer in a parabolic system, or would be the LNA to radiator, perhaps a polarizing part to AESAs. The LNA noise figure is pretty much common. Discrete LNAs can generally do a better job, packaged LNAs, in terms of a lower noise figure than mimics, but mimics are continue to get better. There's the sky temperature, which is of course common to all the systems. So when you roll all that up, you get gain efficiency, antenna noise, which rolls up to G-on-T efficiency. And then there's one more of the bottom two rows I'd like to refer you to, which are the scan loss. So phased arrays, of course, the whole point of using phased arrays is so they can scan. And not all phased arrays have the same amount of loss versus scan angle. So for instance, at 20-degree elevation, that would be 70 degrees from scan for a zenith-based system. Some AESAs may have as much as a 7.5 dB per K loss in G-on-T, which comes from two different mechanisms, which I'll talk about in a subsequent slide. Okay, so drilling down a bit deeper on this chart, and again, generic to all phased array types, we can see the net impact of ohmic loss and LNA noise figure on overall GNT efficiency. The chart on the left applies to active, i.e. the distributed ESAs or AESAs, where there's generally one LNA dedicated to each radiating element or a small group of elements, typically 4. The middle chart and the chart on the right apply to passive centralized phased array types, where there's generally one centralized LNA and one centralized HPA. As compared to the active or distributed ESA architectures, the passive or centralized architectures can enjoy reduced costs, but generally at the expense of lower efficiencies due to the increased ohmic losses associated with the longer and more lossy RF distribution feeds and networks employed in the passive systems. This can lead then to larger sizes and areas in order to realize or recover the same GNT and EIRP performance. As a rule of thumb, each 1 dB of added ohmic loss drops GNT by 2.5 dB. So that's 1 dB of lost gain, but also 1.5 dB of increased noise temperature. So that quotient goes up by 2.5 dB. Similarly, each 1 dB increase in LNA noise figure drops the resultant GNT by 2 dB per K. This means that in some cases, it may make sense to use more expensive, lower noise figure LNAs in order to realize a smaller and lower overall ESA cost on a net basis, simply because you can use far fewer components based on the greater GNT efficiency. Clearly, the ohmic losses in the LNA noise figure are highly leveraged in the efficiency and therefore the size of phased arrays. And that increased size can have additional downsides, including narrower, which are more difficult to point, antenna beam widths, narrower channel bandwidths, which comes from the beam squint phenomena, and higher power demands, which we'll talk about in the upcoming charts. In addition to ohmic losses and noise figures, phased array antennas must, by design, scan the beams, and this can introduce another loss associated with undesired mutual coupling phenomenology, wherein the energy radiated by one radiating element is undesirably absorbed by adjacent elements, particularly at higher scan angles. This is termed as active impedance phenomenology and is additive to the geometric-based cosine loss associated with the reduced projected area of the antenna aperture as a function of scan angle. These two impacts, the former being design dependent, whereas the latter being physics dependent, combine to reduce the overall gain, that is the GNT and EIRP of the SATCOM phased array as a function of scan angle. This particular plot is the measured GNT of a representative phased array as a function of scan angle over a range of K-band frequencies. You'll note that in this case, a cosine roll-off is clearly present, though there is little evidence of any additional active impedance losses. So each phased array antenna type is different in this regard, ranging from a cosine to the 1.0 power, which is shown here, all the way up to, in some cases, as high as a cosine to the 1.6 power. That's the projection loss plus cosine to the 0.6 for the active impedance loss. And so that's an important parameter, particularly in systems that need to scan to large ranges. Okay, overall antenna efficiency drives overall power and cooling demands, and care must be taken not to create a vicious cycle in terms of size, power, and overall resource demand. Lower efficiencies, of course, lead to larger sized antennas to meet a given requirement. We have to make them bigger, which of course generally leads to higher costs. However, larger sizes also necessarily imply more components and or larger prime power dissipation. So if not properly managed, this can lead to higher operating temperatures, which can in turn lead to lower reliability, higher junction temperatures, and or restricted operation at high ambient temperatures. Management of these higher heat loads often requires separate active thermal management. That could be forced air cooling, liquid cooling, heat pipes, etc., which can further exacerbate the prime power demands. And these higher prime power and LRU demands can drive up total system volume and weight, particularly when you consider external support equipment such as power supplies, beam steering computers, and in some cases, separate thermal conditioning units. Here's an example contrasting a hotter phased array dissipating 1,000 watts to 2,000 watts to a cooler phased array requiring only 200 to 500 watts. As you might suspect, power added efficiency in HPA and the power consumed by the LNAs is highly leveraged, i.e. valued in consideration of these power demands. Okay, so we briefly discussed both distributed and centralized architectures For the latter, the power added efficiency of the centralized HPA, which may be solid state or tube-based, depending on power level, can be an important power dissipation and cost consideration. And improvements in these packaged devices in terms of power added efficiency, linearity, size, and cost are important areas of interest. In addition, the centralized approach is ideally suited to simplified accommodation of different desired EIRP levels or frequency plans for a given aperture, i.e. it's a simple replacement. Whereas in a distributed architecture, comprised perhaps of thousands of individual HPAs and LNAs, this may be driven to completely different chipsets and or strong changes to the PCBs and the associated hardware. In terms of practical operational considerations, and specifically in the case of small consumer or enterprise SATCOM terminals, it can be highly advantageous to limit total prime power requirements, such that they're compatible with power over Ethernet, thereby enabling a simple one cable interconnect that can be employed in connecting the outdoor unit or ODU to the indoor unit, IDU, and the modem. Another important SATCOM application, particularly for enterprise users, is in support of remote backhaul of LTE and 4G, 5G terrestrial services via satellite. It's a very hot area. These remote sites can often be prime power disadvantaged or limited. They're relying on solar, battery, remember you have to work at night too, and or generator support. And hence overall power efficiency can again be very important. As a final example, in the in-flight connectivity domain, gate-to-gate operation has become the new norm, i.e. that's the passenger expectation. So specifically with a plane parked at a gate in Phoenix or Dubai in the middle of summer and under full solar loading, the power thermal efficiency of the externally mounted phased array SATCOM system can be critical to ensure seamless operation without thermal safety shutdowns or similar interruptions in operations. As more and more satellites are using and consuming a limited amount of frequency band resources, the topics of interoperability and overall interference suppression are seeing increased concern and regulatory scrutiny. For example, we previously mentioned the Ka band frequencies with SATCOM terminals employing the 27.5 to 31 gigahertz frequency band for SATCOM uplinks. This 3.5 gigahertz of ITU band must be shared by all of the Ka band SATCOM systems. So that's including all of the various GSO constellations from Hughes, Viasat, SCS, Telesat, and others, but also NGSO users, including Telesat, SCS, O3b, mPOWER, Kuiper, and others. And to make things even worse or more challenging, the same 3.5 gigahertz bandwidth is also used or claimed by terrestrial users who employ these same bands for the 5G millimeter wave services, also known as the upper millimeter wave 5G. The challenge then for SATCOM terminal is to focus emissions in directions only where intended, i.e. directly at the intended fixed or moving satellite, and to strictly limit emissions to all other directions, i.e. in the directions of other unintended GSO and NGSO satellites, as well as toward the ground where terrestrial users depend on these same frequencies. This is becoming a very big issue. In the parlance of antennas, this equates to strict limits and control on the side lobe emissions. This chart illustrates the full hemisphere and pattern cuts, as you can see on the left, for a representative phased array at both shallow, that's upper left is a 12-degree scan angle, and it's steep. The lower left is a 75-degree scan angle example. Blue is good in this case because that indicates emissions that are minus 35 dBc or lower relative to the main beam. And this is the type of chart that you want to use to evaluate the interoperability and interference potential of any phased array system. Okay, we've reviewed the various phased array types and characteristics, but what are the markets and platforms in which phased array antennas for SATCOM are being deployed? We'll describe 6 of the major markets. These include aeronautical, including in-flight connectivity or IFC, but also military and government platforms, including fighters, transport aircraft, UAVs, etc. And mobile markets, including both commercial and government comm on the move, man-portable systems, which can be quickly or evenly instantly deployed in remote locations, satellite payload antennas, i.e. the antennas on the satellites themselves, which are key for various functions, including user beams, crosslinks, gateways, and gateway antennas. Those are the big antennas on the ground, typically large parabolic dishes that are used to backhaul the satellites. And then finally, fixed applications. These would include both consumer and enterprise NGSO terminals that are fixed in position, but must accurately track NGSO satellites as they move across the sky. Okay, so in aeronautical markets, we have both a commercial, lower represented in the lower left side, and military or government aircraft shown in the lower right-hand side. The key characteristics here are, of course, how many aircraft you have, but it's really all about the service uptime, which would include all of the issues there when the aircraft's turning and can't make links, when the aircraft is flying out of satellite coverage. But the whole point of course, is to get this to 100% or as close to 100% as practical. Other important considerations include reliability or mean time before failure. That's very key on aircraft, both on military aircraft, but also particularly on commercial aircraft where it's expensive to take a plane and put it in the hangar to replace the satellite antenna. So it's important that you have high reliability from the get-go. In mobile markets, these would be the COM on the move markets. Again, there's both military and commercial applications. And kind of shown on the bottom here, you could have civil or government systems that need to be able to do disaster preparedness, first responders, be able to work from the field and actually on the move. There's traditional military applications. And of course, there's maritime markets as well. This could be super yachts in some cases. And of course, this could be naval vessels in other cases. In terms of portable markets, these need to be very lightweight because by definition they're portable, but these are going to be used for high-speed internet access from very remote applications, obviously where you're not going to be getting a 4G or 5G signal. These have to be able to exploit both wide beam and high throughput satellites. And they need, the main attributes is they need to be really fast or easy to align and stabilize. Ideally, they should align themselves. Space payload markets, well, these are have various functions. These are the antennas that are actually on the spacecraft themselves. These could be extremely small because satellites come in all sizes. They come from 3U satellites, which would be roughly the size of a loaf of bread, up through nanosats, small sats, and of course, traditionally the larger satellites as well. The key characteristics here are to reduce power again. Again, prime power is in very short supply particularly on the smaller satellites. But of course, weight, kinematics, and high reliability, particularly you would like to have systems that don't have any risk with respect to being deployed, as might be the case in gimbal parabolic dishes. And we have the gateway markets. So gateway markets, again, the idea here is to use phased arrays to replace what have been traditionally large 2-meter to even 11-meter parabolic dishes. There's several different approaches to do this, but generically speaking, the idea is to use the phased arrays, and then in using the phased arrays with their beam agility and the ability to reconfigure, you can have then what would be reasonably termed a software-defined gateway system, where you can use one unified system to replace many parabolic dishes, perhaps 2 dishes or 4 dishes or even 8 dishes, and in a much lower profile, lower wind loading condition. So this has many advantages, and there's a lot of movement in this market currently. LEO and MEO user terminal markets. Well, we mentioned the Starlink terminal has enjoyed some adoptions. It's in beta distribution right now. A good part of this market is and probably will be done by parabolic dishes. And here we're showing a pair of parabolic dishes because oftentimes you want to do a make before break in these markets. So you want to be able to be on the next satellite, if you will, before you have to release from the next satellite. And of course, there are many ESA approaches to solving this problem as well. Okay, so let's summarize. What are some of the important factors when choosing a phased array? Well, we talked about LEO, MEO, and GEO interoperability. I think this is really, there's not many users who want to deploy a LEO only or even a GEO only solution. The trend here is now to go to an interoperable system. We talked about reliability. That's obvious in commercial aircraft, but reliability is key in all applications. In some cases, we may be embedding these antennas inside an aircraft or inside an enclosure, for example. That's happening right now. And in doing so, I already mentioned the thermal and the heat concerns, but reliability as well, because generally it's going to be very costly to have to replace these units or to service them after they've been enclosed. We talked about size and spectral efficiency. Generally, the higher the G on T, the higher spectral efficiency, and the overall G on T efficiency is the key parameter for judging the size of an antenna for a given G on T requirement. We talked quite a bit about power, and we also alluded to minimum elevation angles. antenna can work effectively at very low elevation angles. That gives you more flexibility, particularly on a moving vehicle, to work larger constellations in different types. And then wide instantaneous channel bandwidth. We talked about frequency bands. We talked a little bit about Q and V band, but this is really referring to the channel bandwidth, that, the bandwidth you would see on the spectrum analyzer, if you will. Used to be 36 megahertz in the SATCOM domain was sufficient, but this has quickly moved to 125, and really 250 megahertz has become the norm right now. And we can see that pushing to 500 megahertz. And in some cases, in some military systems or HOP systems, this has grown to 1,000 gigahertz, 1,000 megahertz, or even 2,000 megahertz. Okay, so bottom line, how does this impact LNAs, HPAs, and RFICs? Well, we talked about the need to move towards extended availability in these higher frequency bands. Those are Q band, V band, but also E and W band. We like to have higher power efficiency for the reasons I already mentioned for both the LNAs and the HPAs. Reduce front-end loss in single and also multi-element packaging, particularly in RFICs. This is an important metric. We talked about that relative to the impact, particularly on G on T. Lower noise figures are always better than higher noise figures for LNAs. And I mentioned that the LNA noise figure is highly leveraged in the size and cost of the system. And of course, the LNAs themselves would prefer to be in a cooled situation. So we need to improve thermal isolation of the LNAs. We like to keep them cool and well isolated from any heat generated from the HPAs. We're moving to higher power densities for the HPAs. This is a trend to be able to support the higher EIRPs and higher data rates. We alluded to improved heat sinking and cooling techniques, and there's a lot of creative solutions coming in that area. Improved front-end protection. I didn't mention too much about that, but particularly in cases where the LNAs are distributed, maybe we have 1,000 LNAs, they need to be resilient to be able to operate through and survive high EMI and EMC conditions. Improved linearity, which would equate to a reduced backoff in the HPAs. Linearity is always important, and as we move to higher and higher modulation codes that demand higher and higher linearity in order to keep the fuzzballs, if you will, small, this is going to continue to push on linearity requirements for HPAs. And then lower cost and higher volumes. We're finally seeing some very high volume applications, and it'll be important to be able to scale KU, KA, and eventually Q and V bands to cost to meet these high volume, low cost targets. So I want to thank you for your time. I hope this has been somewhat educational. I appreciate the opportunity to speak with you, and look forward to any questions. You can feel free to send those questions to me. I've provided my email address below, and appreciate your time.